Good afternoon. My name is Ed Franklin. I'm an associate professor in the Department of Agricultural Education at the University of Arizona. Today we're going to discuss solar principles in terms of how a module works and how we can test a module, and then later we're going to look at different solar pumping systems. Solar modules or panels are made from silicone, and they absorb the photons from the sun and take the electrons and convert that into electrical energy. If we take a look at the back of a solar module, we have a junction box and we have a cable coming out with a positive and negative conductor. These are our leads that we will be using to move electricity collected by and produced by the solar module into our system. Solar panels or modules come in different sizes, and they are rated by the maximum power. This particular module is rated at 20 watts. So it is designed to produce 20 watts of power at maximum potential. We see that we have an operating voltage. So for this particular module is rated at 17.2 volts. And we have to remember that this is DC or direct current electricity. Also, this particular module has an operating current maximum power of 1.16 amps. Our open circuit voltage, and we'll demonstrate how to measure that on this particular module, is rated at 21.6 volts. And the short circuit current is rated at 1.31 amps. Let's talk about Ohm's law for just a moment, which is an opportunity for us to look at how we measure electrical power. Watts is a function of volts and amperage. So if we take 17.2 volts, multiply it by 1.16 amps, we'll come up with roughly 20 watts. Now all panels are measured using standard test conditions. So the rating of 20 watts is at a standard test condition of 1,000 watts meters squared at 1.5 atmospheres. Ideally, we like to look at where our location is in the northern hemisphere and set our angle of our module so it's perpendicular to the sun at the highest point of the day, which would be around 12 noon. In Tucson, Arizona, our latitude is 32 degrees. So we'd like to set our module at 32 degrees. So using a pitch or angle finder, if we can set this at approximately 32 degrees, at about this time of day, we should be at the optimum of receiving the most sunlight to produce maximum power. To measure the amount of sunlight or radiance, we're going to use our pyranometer. So setting our pyranometer so that the top end is facing towards the sun and at an appropriate angle, we can see how much energy in watts per meter square we are collecting. At this point, at this angle, we are receiving somewhere almost 1,000 watts per meter square. As I increase the angle, we can see that the amount of irradiance decreases. So it's important that when we set up our modules, that we find the ideal angle. So at the peak sun hour day, which would be from about 12 p.m. to 1 p.m., we can maximize on the most irradiance available. So we've already talked about proper angle towards the sun, and we've talked about watts per meter squared. So now let's look at how do we measure open circuit voltage and short circuit current on our module. The tool we're going to use today is a digital multimeter. What we're going to do is take the test lead from the digital multimeter, in this case our positive lead, and we're going to connect it to the MC3 connector coming off our module. We will also connect the black or negative lead to the negative wire coming off our module. We're then going to turn on our meter measuring voltage. Now notice we have a very low voltage meter, approximately 11.6 voltage. And that's because our module is not facing the sun. So let's see what happens to our reading when we turn our module facing the sun. So right now, let's take a look at our open circuit voltage. We have our test leads connected to the wire leads coming off our module. And right now we see we are receiving 19.71 volts, and that's open circuit voltage. What happens when I adjust the angle? Well, we see the voltage starting to decrease. So this goes back to our discussion earlier about angle. If we can maximize the proper angle, and with the amount of radiance, we can increase the amount of voltage that we're able to produce from this module. So let's go back and take a look at our module. It's rated at 21.6 volts, but the reading on our digital multimeter was less, 19.7. One of the things we have to take into consideration is temperature. The hotter the temperature, the less voltage our module will produce. So let's use an infrared thermometer and measure the temperature on the back of our module. Right now we're getting a reading of 120 degrees Fahrenheit. So this is quite warm. Think about a module that's mounted on the top of a roof where there is very little space for air to circulate. The hotter that module gets, the lower the voltage it's going to be able to produce. Now let's take a look at measuring short circuit current. To do this, we're going to connect the ends of our lead together, and we're going to use our digital multimeter. We're going to turn it on to DC amps, and we'll always start with the highest and work our way down so we don't damage our instrument. We're going to zero it out, and then we're going to clamp it over our positive conductor. So now we're taking a reading on our short circuit amperage, and we can see with our clamp-on meter we have it clamped around one of the leads. We have both the leads connected together, and we are obtaining a reading of 1.41 amps. As we adjust the angle towards the sun, again, we can see what happens to the amperage. So we are receiving about 1.74 amps is the maximum at this particular angle. So let's put our module to work. What we're going to do is demonstrate a direct DC or direct current system. What we have here is a pump in a bucket, a 12 volt or DC powered pump, and we're going to move water through a line and recycle it back into this 5-gallon bucket. And the power to turn on this pump will be provided by our module. Let's take a look at the leads coming off of our bilge pump. What we have connected here is a fuse rated at 2 amps. And our leads are going to be connected to leads that we can connect to the back of our module. For safety, we would always like to make these connections while the module is face down or out of direct sunlight. Now we will take our module and face it towards the sun, and we'll see what happens. Let's see what happens if we adjust the angle of our module. As we can see, when our module is not facing directly into the sun, the pump does not pump at its full capacity, which means less water is moving. So for this pump to work at its capacity, we want to make sure our module is set at the best angle to get the most sunlight from the sun. Let's bring in our meter again, our pyranometer, to look at irradiance and how much we are actually obtaining when we're set at this particular angle. One of the things that can happen if we don't have our module set up correctly is if we get shading. Let's see what an impact shading has on this particular module. I'll use my hand to represent leaves of a tree. As we can see, as we have shading cast across the module, it affects the performance of the module. This DC powered pump is variable voltage, which means that the pump will work at full capacity when the module has full access to the sun. When the sun goes down at the end of the day and there is no power for the module, acts just like the shading, the pump will stop working. Let's talk about another solar pumping system. This particular module is rated at 85 watts with a maximum operating voltage of 34.4 volts and operating current of 2.47 amps. We have a junction box and we have two leads coming out of that junction box, and again they are labeled positive and negative. These leads are connected to connectors, and these leads then move into what we call our direct current disconnect box. We're now going to move from the module and talk about our balance of system components. Since we're dealing with electricity, safety is our utmost concern. You can see I'm wearing safety glasses before I do any work. Also, you'll notice that our module is in, or disconnect is in the off position. Right now, this module is producing electricity while it is pointed to the sun. Now we've got our disconnect box open. Let's take a look at where the leads are going to. We can see our red line is our positive, it's coming up to a lug. We see our black, which is our negative, is also connected to a strip down below. And we have a green wire, which is our ground, is connected to the box. Let's see what kind of voltage that we're able to get at this time. So we're going to use our digital multimeter to measure the voltage that is being produced on our module at this time. We'll turn it to DC volts. I will put my positive lead at the positive lug, my negative lead at the negative lug, and at this time we see that our module is producing 38.0 volts. If we trace our lines, we can see that our positive line leaves our box along with the negative lead and comes over to our pump controller box. Inside our pump controller box, we can see that we have our black and our red, which are our negative and our positive leads, connected to the controls representing PV negative and PV positive, standing for photovoltaic. We can also see that our green wire conductor is connected to the ground lug in our box. Let's take a closer look at our pump controller. We have indicator lights here that tell us if we have power coming in, power going out, a remote switch for our pump, and overcurrent and low water cutoff. At this time, we have no power going to our pump controller. Let's go ahead and engage our switch and take a look at our controller. Now we see that our red light indicator is on, which means we have power coming into our pump controller from our module. And we can verify this using our digital multimeter. Placing the red on the positive, the black on the negative, we now see that we are receiving 38.26 direct current volts from our module. Let's take a look at our submersible pump. The model is designed to be fully immersed inside a pipe or wellhead casing. It consists of a body with a motor and an intake port near the top end. The discharge pipe comes out the top of the pump. Today we're going to be using a 3/4 inch PVC pipe. This pump is rated maximum direct current voltage of 30 volts. So this pump is sized up with our PV module. Our waterproof safety line is connected to our discharge pipe using plastic zip ties. If we take a look at our electrical lines coming off of our pump, we see we have a red, black, and a green line. These conductors represent our positive, negative, and our ground conductor. They are connected with a shrink wrap connection. To monitor the level of water going into the pump and out of the well casing, we have a remote valve device. As this raises and lowers with the water level in the pipe casing, it sends a message to the pump controller to turn on or off the pump when the water level is high or the water level is low. Let's talk about the rest of our system. In a deep well, we'd have a discharge pipe that would discharge the water from the pump all the way up to the top of the wellhead or well casing. The water would then leave the pump, go through a discharge pipe or line, and over to a storage tank, or in this case, a livestock watering trough. Our PV-powered livestock watering demonstration system consists of a 100-gallon Rubbermaid water trough, a water return line, an 18-inch PVC pipe that represents a cistern. The first thing we're doing is connecting our discharge or return line, which is braided 1.5-inch poly tubing with a banjo or cam lever coupling. We'll now connect the opposite end to our cistern. At this time, we're going to complete the setup of our demonstration system. I'm going to go ahead and submerge our pump into the cistern. And now we'll connect our electrical leads to our system. Before we make any of our connections, we want to make sure our system is turned off. We've insert our leads through the bottom of our control box, and now we're going to go ahead and connect each of the conductors. Anytime we're working around electrical systems, and if we're going to be away from the main disconnect, Ideally, it'd be great to provide a system of locking out anybody who may potentially turn on or engage the system while it's being worked on. Today I'm going to use a special lockout lock and hang on to the key while I'm doing the work to make sure that no one can energize the system while I'm connecting the components. The system is now locked out, and this will prevent anybody from turning on the system while I'm trying to make the connections. Let's take a look at the connections that will be made in our pump controller box. Once again, we have our leads or conductors coming from our photovoltaic module. The negative lead is connected under the PV negative. The positive lead is connected under the PV positive. We're now going to connect the positive lead from the pump and the negative lead to the pump under what we call the line on the pump controller. To connect the leads from the pump, we're going to use load negative and the load positive terminals on our pump controller. Once again, with the power disengaged, I'll use a screwdriver to back out the connection, screw, and attach the end of the lead to the terminal. All of our connections are snugly attached to the terminals. Now we're going to connect the leads to the remote switch. We will back out the terminal connection screws and insert the bare ends of the conductors under the terminal ends. Look to make sure that our leads are snugly connected under the terminal screws. Now we're ready to engage our system. If we look inside our pump controller box, with our system energized, we should be able to see a red indicator light, which tells us that power is coming into the box from our photovoltaic panel. Let's verify this using our digital multimeter, setting it once again to DC volts. We'll first take a look at our photovoltaic panel to see how much voltage is coming into our system. At this time we have 38 volts. We can also take this look and see how much power will be going out to our load, which is our pump. We're going to connect or place the leads of our digital multimeter on the connecting screws. At this time we have no power going out because the switch is in the off position. Let's go ahead and turn on our system to see if our pump is actually operating. So moving our switch into the up position, we can hear the pump is actually moving water at this time. Let's verify this taking a meter reading on the load terminals of our controller. We can see that 29.18 volts of DC power is going to our pump at this time. Once again, the maximum DC voltage on this pump is 30 volts. Taking a look down inside our wellhead, we can see our pump is fully submerged under the water, and our black remote valve is floating on top of the water. The pump is actually moving water through the discharge line and out into our water trough. In an actual pumping situation, water will be discharged or drawn from the lower end of the well. At a certain point in time, we do not want our well to run dry. So we need to have a way of turning off the pump until the well is able to recharge itself. That is the role of the remote switch.
You can tell by the flashing light that the cutout switch for the float is still active.
To demonstrate how the remote switch operates, we're going to shut off the flow of water returning from our trough into our cistern. This will replicate a well actually being drawn down by the pump. In a few moments, our pump should shut off as the remote switch will drop down at a preset level and send a message to the pump controller. At this time, the remote switch cut off and sent a signal to the pump controller indicating the water level is too low to continue pumping. The pump is now turned off, and an indicator light is illuminated on our control panel. Let the float re-engage and turn back on the pump. This is an example of a direct PV system where the power from the module is flowing directly to the pump to provide power. The pump will only run when the sun is shining. But what happens when we have cloudy days? Or what happens at night when the sun is not shining? The water trough will not fill. So what do we do as producers at that time? When we have cloudy days or the sun is not shining, we still need to get water to our livestock. This is why a producer might look at investing in some type of storage tank, so 2 or 3 days supply of water can be kept on hand in case it's cloudy or your system is not operating. But what about at night and on times when we have cloudy weather for a long period of time? How do we get power to our system? Well, let's talk about stored power using a battery. A second type of solar powered system is with a battery backup. The components of this system are very similar to what we worked with previously. The only thing different is that we've added a battery for power storage. This particular example we're showing you is a water collection system. This cistern holds 2,000 gallons of water collected from the rainfall on the roof of our laboratory building. Inside the cistern is a submersible pump, very much similar to the one we worked with earlier. The water is pumped from the cistern to provide water for our irrigation. Let's take a look at the components of a battery-based photovoltaic system. Let's start with our PV or photovoltaic module or panel. We have a single panel mounted to a pole, angled in a southerly direction at approximately 32 degrees latitude. Our wires are fed down through the pole into our control box. Here we have a solar charge controller. The solar charge controller monitors the amount of power produced by the panel so the batteries are not overcharged. To store the electric power that we accumulate from our photovoltaic module, we have 2 6-volt golf cart type batteries. To protect them from the elements, we have them encased in a plastic marine battery box. Let's go ahead and remove the cover and take a look at our batteries. Okay. Inside our battery case, we have 2 6-volt deep cell charging batteries. These are the type we would see on a golf cart. They are connected in parallel. So instead of 6 volts, we now have 12 volts. This is a series wiring pattern. In a series system, we have the negative terminal of one battery connected to the positive terminal of a second battery. What this does, it doubles the voltage. So instead of having two 6-volt batteries, we now have 12 volts. Let's trace the conductors from our batteries to our system. Our negative and positive cable come up into our box and are connected to the battery terminals on our solar controller. The purpose of the solar charge controller is to prevent the battery from being overcharged. The other cables coming off of our solar charge controller go to our sun pump controller. Again, a controller very similar to what we saw in our other demonstration. The cables coming in from our photovoltaic panel are also connected to the charge controller, and leads are connected to the pump controller. The third set of leads are our load leads and go to the submersible pump housed in our cistern. Okay. Let's take a look at the indicator lights on our system. The yellow power on indicates that we have electricity coming in from our photovoltaic panel. Our red indicator indicates that our battery is fully charged. And our green indicator light indicates that we have electrical power moving from the system over into our pump controller. We can tell by the red indicator light on our pump controller that we have power to the system. Let's flip the switch and see what happens. Right now our pump has been turned on, and if we look over at our irrigation system, we can see water being pumped from the cistern into our planters, providing irrigation water to our plants. The advantages of a battery-based system is that we have stored electrical energy available to power the pump to provide irrigation water to our planters, even when the sun is not shining. This is critical on days where it is cloudy, or if we want to irrigate our plants at night. Let's take a moment to discuss what we've already looked at today. We've talked about solar module and how to measure a solar module for power, voltage, and amperage. We've talked about a PV direct system, where a module sends power directly to a load, such as a pump. We've also talked about what happens when we add a battery to the system. We're able to store electrical energy and use it for times when we do not have the sun shining, such as at night or on cloudy days. A rainwater harvesting cistern, such as this galvanized system behind me, is a great way of collecting water off your roof to irrigate your pastures or your lawn or your garden. This particular system is very simple in that there is no pump to move the water. Gravitational water flows from the cistern through the faucet and out this hose to provide water to the garden or the lawn area. I would like to spend a little bit of time talking about water collection systems. This particular water collection system is made up of a galvanized cistern. Water is collected off the roof of this building using a gutter and conveyed through pipes. Now, to remove the dust and debris that occurs on the roof before the first storm, we use what is called a first flush system. Water is collected and transferred from the gutter down the 4-inch PVC pipe. A plastic ball inside the pipe will float to the very top of the T. Any new water coming off the roof will then flow through the pipe and be deposited into the cistern. The advantage of this system is we can remove dust and debris off the roof from the first storm before it gets into our collection cistern. Periodically, it is important that we do some maintenance on our first flush collection system. What we're going to do is remove this cap and remove any water and debris that collected after our first storm. I will carefully untwist this, as you can see there is a considerable amount of debris in the water. Yeah. Okay. Let's see. After we remove the cap, we can see that there was a considerable amount of water stored up inside our first flush system. When the water has filled up to a certain point, this black plastic ball floating on the water seals off the system. Any additional water coming into the system is then transported into our storage cistern. This keeps our cistern clean and removes any debris such as reptiles, sediment, or vegetative matter getting into our system, which may end up clogging our irrigation lines. To access water from our cistern, we have two 3/4 inch hose bibs that are plumbed into the system. The outlet lines on this system are 4 inches above the base of the cistern. This prevents any dirt or sediment from getting into our water line. This particular rainwater harvesting collection system has a valve which allows us to release any stored water so that we may go back in and clean the system if we need to. Also, there's an overflow valve inside the tank. Any excess water flows through that and bubbles up through this outlet valve. This keeps water from flowing over the top of the cistern. In a gravitational rainwater harvesting collection system, the amount of water or pressure that we have available at the end of our hose is dependent upon how much water we have in our system or how high the cistern is above our actual hose. If I raise the end of this hose up, we can see what happens to the available water and water pressure. This is an indicator that there is very little water stored in the system. If I bring the hose back down again, we can see the water begins to increase and the flow increases as the water level of the hose is lowered. To summarize a little bit of what we've talked about with rainwater collection cisterns. Our system is designed to collect the water that is captured off of a roof and conveyed to the cistern using a gutter and collection system. The water can be filtered using a first flush diversion system. That is a way of removing any dirt, debris, vegetative matter, or byproducts before it gets into the cistern. We can remove water from a cistern either directly using a hose, or we can use a submersible pump to move the water into an irrigation system. Today we've had an opportunity to share with you information about solar photovoltaic systems, including a very simple direct system, a more complicated direct system, a battery-based system, and some information about rainwater harvesting. We hope we've been able to answer some of your questions about photovoltaic and solar water pumping systems. We hope that you have an opportunity to investigate how some of these systems might work for you. Thank you for taking the time to view our video today. For Steve Poe behind the camera, I'm Ed Franklin from the University of Arizona. Thank you.